Hey everyone, it's Mike from IOPipe again. For those not familiar, I'm our senior site reliability engineer who keeps the lights on running our backend infrastructure. For the video today, I wanted to do something a bit more basic, but something that is a basis for a very powerful advantage for developers to write performant code, to save cost on Lambda execution time, and right-size your Lambdas. This is our CPU profiling feature, profiling the execution of the code as it happens. All right, first things first. Let me give you a quick rundown of what I'm doing and how I'm doing it in this video. In the typical use case of IOPipe, you're going to be importing our libraries into your code base. And in this one, you can see I'm doing the profiler plugin. And then where I'm instantiating IOPipe, you can see I just added this plugin profiler enabled true. You can do this through the code, which I'm doing here, or you can also enable this through the Lambda console if you just want to turn it on for a very short period of time. From there, I'm using a crypto library, and in this code base, you can see here I have two different functions where I'm hashing out passwords basically. And I'm using two different portions of the crypto library. You can see the PBKDF2 sync and then the PBDKF2 regular. And so I was actually just testing the difference between asynchronous and synchronous calls inside Node. All right, so now that we know what the code base is doing, the two different functions that I'm using, we can go ahead and move into the IOPipe dashboard to show you exactly what I'm doing with profiling. As you can see here, I'm in the individual function here. For the sake of the video, I've ran the function multiple times using the two different functions. And I've also changed the size of the lambda, so the memory tier that you're giving it, just to kind of show you exactly what's going on. So the first portion that we're going to take a look at is going to be the profiling that you get for when you run an asynchronous call with a 1500 megabyte memory tier. And so I'm going to jump into the function that you see here. So when we go to the next page, you're seeing the individual function information that ran at the current time. I did some tracing of the code, so instrumentation of the code inside the code base I'm using, just to kind of pull out what's going on from a very high level. You can see the regions that I executed in, the metrics for this specific run, and then also some custom metrics. I wanted to make sure that if it did succeed with the password hash, it returned that to me. If we scroll to the bottom, now what you're going to see is this new area. So we have the plugin enabled, and this is where you can download your profiling information. A caveat here is that we are pulling this information in shortly into the dashboard that you see here, but that's a very opinionated thing. Some developers like to use external profiling tools. I use Chrome Inspector personally. So what we can do is we can go ahead and download this profiling data. So we click here, it downloads a zip file, and then we move on to our profiler. So now we're in the profiler. I unzipped the file, I loaded it into Chrome Inspector, and now I want to see exactly, what's going on with the function itself, what it's doing, how long it's doing it, which lines of the code are doing it. I like to think of this is kind of the old is new concept. So profiling used to be really prevalent, 10, 15, 20 years ago. But as the hardware advanced, this kind of stuff went to the wayside a little bit. I mean, there's still a lot of people doing this because they really care about, down to the microsecond of what's going on inside your code base. But when, the prevalence of VMs and all these things, they proliferated, this kind of went to the wayside a little bit. So now it's making this comeback because with Lambda, you're only paying for your execution time. So you really want to get that execution time down as low as possible. It saves a bunch of cost in the end. So, this is definitely making a comeback, and I love it personally for our own production infrastructure. But for this demo video, we just executed, this password hash function, and we want to see what's going on inside of it. And so now we're looking at the profiling data that comes out. So this is the CPU profiling data. Not much to see here because this is the asynchronous version for Node. So what we're going to do, you can kind of see some blips on the flame chart here at the beginning, middle, and end. And so we want to understand what's going on there. So I'm going to zoom in here, and we're going to scroll in a little bit. So now what we're seeing is every single execution that the code was doing. You take a look here, I mean, you can see where it's instantiating IOPipe, but you can see where it's pulling in the actual library for the PBKDF2 crypto library. It's setting up all the stuff to do the execution of the hashes. We go from here, it's doing some buffers on the strings. You can see, what line of the code inside the library that it's running, how long it's running. You got the fast buffer, you got the unit 8 array constructors, all the code stuff that you ever want to know. But the best part about this, it gives you how long it took and the line of code, that's taking the longest. So when we were just looking at like importing the library, if that was taking an excruciatingly long amount of time, you could say, well, maybe that library is not optimized, maybe it's not performant. You can pull in different libraries, see how it affects the code base, and so on. So in the case of asynchronous, this whole beginning portion of the code is the crypto library setting up the event loops that it's going to do all the hashing. So it's going to do all this asynchronously. So when you're looking at it, you come in here, okay, well now we got all this idle time. So the idle time that you're seeing here is basically the I/O of the system. It's taking all the event loops that were generated from the password hash. It's starting to crunch them. There's a little bit of overhead associated with that, and now we just have to wait. This is a very heavy, function. It takes 16 seconds to run. If we take a look at the middle, you can see where the code is executing some more portions before it adds more to the event loop and does more password hashing. So, okay, well, socket destroy, socket close, all the typical stuff that you'd see. This is very performant, but there's a ton of idle time. And then if we look at the end of the function run here, you can see this is where the promises are all finishing, everything's coming back, it's returning everything to the machine, and finally it's putting out the password hashes basically into the console of what we're outputting right now. Very typical use case. You can also change some things around here to take a look at some different items. So if you go from the heavy bottom up, this will give you a kind of a list chart here so you can exactly see what's going on. Again, this is a little bit easier to read instead of that whole time flame graph. But you come in here, and like I was talking about, you can see where it's importing libraries. It's taking 28 milliseconds here. In the case of a different crypto library, it's taking 146 milliseconds. So using this one was a little bit more performant as it's setting up the event loops to do the password hashing. This is very basic stuff, like for the video, as I was saying at the beginning. I just want to give you guys an understanding of what's going on and kind of how to use this. And then in future videos, I'll show you how to use it more in an in-depth fashion. But this is really straightforward stuff, but it's super important if you start thinking about how the libraries, the importation of the libraries, these types of things are affecting how long it takes to run the code, how long it actually takes to execute setting up of the event loops, how long it's sitting there waiting for the I/O to return to the system, and so on. Now, if we switch to a different profile, so I had a second execution where I went from the asynchronous password hashing to the synchronous password hashing. So this is a different portion of the library, and so we could take a look here. So I'm going to jump back to the chart over here, and we're going to zoom out here, and then I'm going to load this second profile. Right off the bat, this one looks a lot different. And so now we're starting to understand the difference between how it's executing the code asynchronously versus synchronously. So in this case, we have some of the similar information at the start of the function, but the actual crypto library itself is locking the function into synchronous mode, basically, and it's executing over the entire duration of the function run. And one thing you're going to notice here, we executed down to 11 seconds. So that was a full, 5.5 second drop by doing this synchronously. Typically in hashing situations, when you're doing synchronous calls, it's a better use of I/O for the system. And when you're doing it asynchronously, there's going to be more overhead from event loops and the such, from the language itself. And so this was a very good way to understand exactly what the code's doing over the entire life cycle, and understand that, yes, in this case, a synchronous password hash call is faster than the typical asynchronous, node version. So I would typically do this in a different language, but this was just kind of an experiment just for the video to see what's going on. The next thing that I wanted to show was, what happens when you change the memory tier. So I went back to, the asynchronous version of the application. And so if we remember at the beginning here, it took 16 seconds for this to fully finish. So now with the profiling, I can go in and check out this third execution run. And what you see here, so this is the same exact portion of the code base. And if we take a look, it took 60 milliseconds to set up the event loops for the password hash. If we go back to the original one, you can see here, if we scroll down here, it actually took a little bit longer. And that's an interesting case. So you're seeing that while, yes, the lower memory tier set up the asynchronous event loops faster, when you take a look at the actual processing time, it was, exponentially larger. In this case, it went up to 45 seconds. So if we zoom out, we can zoom to the end here. And when it's starting to finish, close the event loops, return the password hashes, you can see, right here, it's 45.6 seconds. That's a long time. And so this was going from a 1500 megabyte memory tier to a 500 megabyte memory tier. So this is where you can start understanding and using CPU profiling to get a measure of, is a larger memory tier going to benefit me in the long term, cost wise and performance wise, because that's one of the things that you want to balance. So this is just stuff you got to play around with, try out, start relearning CPU profiling and the such. We also offer a memory profiling feature, which I'm going to demo in another video as well. So you could track down things like runaway variables, things that are locking a bunch of memory inside your code, and you can combine both of these to make the most performant code that you possibly can to really increase the performance of your application, but in the end save a lot of money with Lambda. So very short video, guys. Just wanted to really go over kind of the basics of what profiling is. I know this is kind of a generic example, but I will go in depth in some more videos later down the road. If you have any questions or you need any help with setting this type of stuff up, feel free to reach out to me. It's mike@iopipe.com, or you can reach out to me in our community Slack channel, which you'll see in the slide right here. So thanks for taking the time to stop by, everyone. Look forward to any questions, and I look forward to putting out some more videos for you, a little bit more in depth than this one, super high level again. But everybody have a good day, and I'll talk to you later.